Next presentation. It's from the research track titled Improving Shortest Plank Vulnerability-aware Adversarial Training for Robust Recommender Systems.
Hello, everyone. I'm Yunfan, the third author of this paper from the Kaike Laboratory of AI Safety at the Institute of Computing Technology, Chinese Academy of Sciences. Today, I'm presenting on behalf of the first author, Kaike Zhang, to share our work titled Improving the Shortest Blank Vulnerability-aware Adversarial Training for Robust Recommender Systems. Okay, thank you. I will be discussing our research through the following key points. The first is, let me provide you with the background of our study. Okay. Recommender systems plays a vital role in helping users narrowing vast amount of information in their daily lives. However, due to their openness nature, these systems are highly susceptible to poisoning attacks. In practical, attacks typically inject fake user profiles to manipulate the traffic distribution in the recommender system to promote specific items. This can not only degrade the user experiences, but also threaten the long-term viability of the recommender systems. Existing defense methods against these poisoning attacks fall into two main categories. The first category is detection-based defense methods, which focuses on the identifying and eliminating the potential attackers. However, detection approaches often rely on the assumptions of the fake user's behavior, such as clustering, or they may require some supervised attack data to training a classifier model to find and identify the potential fake users. As a result, the effectiveness of the detection-based method is limited by these assumptions that may not hold in real-world scenarios. And the second defense strategy is adversary training. This method adopts a min-max gain framework, introducing adversary perturbations to the model parameters of the recommender systems during training to defend against the adversary attacks. This approach is both general and effective in real-world cases, as it does not depend on the priori knowledge of the attacks. However, adversary training assumes that the attacker may want to significantly degrade the performance of recommendation that it may not hold in the cases. In reality, we found that only a small percentage of users are affected by the poisoning attacks due to the budget limit of attackers. In this way, applying uniform large magnitude perturbations for all users may shield them from attacks can negatively affect the users who may not vulnerable to attacks. Conversely, if we apply small magnitude perturbations to all users, that may not offer sufficient protection for vulnerable users. Therefore, we find that uniformly applying perturbations across all users may not be an optimal solution for adversary training in defending against poisoning attacks. So to overcome these issues, our objective is to develop an approach that applies user-adaptive perturbation magnitude during adversary training in recommender systems. For vulnerable users, we are applying sufficient perturbation large magnitude perturbations for them to issue their robustness, while for users that are not vulnerable, To attacks, we reduce the magnitude of the perturbations to these users to avoid the unnecessary performance degradation. Okay, to implement this idea, the first step is to identifying which user is vulnerable while which user is not vulnerable. This is not a simple task. Okay, we began by examining whether the user vulnerability is static or flagrant. If the vulnerability of users is static, it is that we can explore the statistical features in the training data to identifying the vulnerable users. But if the vulnerability is fluctuant, we may uncover the training dynamics during the recommender system training process to find the dynamic vulnerable users. To explore this, we conduct experiments using a toy example on Gawala datasets. We train a model for 300 apples and collecting the data during each 30 apples to examine the impact of attacks on all users. Our findings are as follows. First, we find that the majority of users were not affected by the attacks. And second, there is no users that consistently being affected by the attacks. And third, the vulnerable users were affected at varying frequencies. That is to say that many people can be affected by the attacks while many people be affected by the attacks with small numbers, and this indicates that the user vulnerability is dynamic. To validate this, we further analyzed the transition in users' attack-affected status. We found that the users who were impacted affected undergo several state transitions. That is to say, if the user is vulnerable in that apples, they may be invulnerable in the next apples. So this confirms our findings that user vulnerable is fluctuant. With this knowledge, the next step is to identify which user were vulnerable. The most relevant metric during training is the training dynamic, is the user's training loss. So we analyzed the correlation between user training loss and their vulnerabilities. The chart on this screen shows the proportion of vulnerable users in each loss bin. We observe that users with lower training loss tend to be more vulnerable than other users with high training loss. Similarly, examining the number distribution of vulnerable users, we find similar results that well-fitted users are more likely to be vulnerable. Why does this happen? There is an intuitive explanation. We find that the poisoning attacks tend to destroy the system's fitting mechanism by creating misleading correlations between users' historical data to the malicious items. And this correlation may involve intricate patterns like high-order connections. So a case study helps us to illustrate this. There is two users. One is well-fitted and one is unfitted. And we found that the well-fitted users increase the likelihood of malicious links that are captured by the recommender systems, making them more vulnerable. Based on this insight, we propose a vulnerability-aware function G to estimate user vulnerability. As shown on this screen, this function evaluates a user's vulnerability based on the loss distribution during the training process. And using this function, we can apply perturbations with different magnitudes depending on each user's vulnerability. Now let's evaluate the performance of our proposed method, VAT, that is Vulnerability-aware Adversarial Training. We evaluate our method with two backbone models, MF and NightGCN, on 3 datasets and compare our methods with many baselines, including detection-based and adversarial training-based methods. And we evaluate our defense performance against several attack methods, and we use the commonly used metrics. Our results show that VAT significantly reduced the attack success regard to the target hit ratio and the target NDCG. We reduced the NDCG by 21% and the hit ratio 22% respectively. And we also evaluated the effect of each method on recommendation performance. VAT also produced best improvement in recommendation quality. Additionally, we conduct a hyperparameter analysis about the initial perturbation magnitude rho. We observed that there is a steady improvement in defense as rho increased, and even with a small value of rho, VAT significantly enhanced recommendation performance. And regarding the adversary training weight lambda, both defense performance and recommendation quantity stabilized when lambda exceeded 1. And lastly, we conduct a case study comparing invulnerable and vulnerable users. When we apply uniform small magnitude perturbations in traditional adversary training, we find that they can preserve recommendation quality for invulnerable users but offer insufficient defense for vulnerable users. And when we apply large magnitude perturbations, uniform large magnitude perturbations, they can protect users who are vulnerable, but they may impair the recommendation quality for invulnerable users. And when we apply the user adaptive perturbation by VAT, it can optimize the recommendation quality for invulnerable users while providing adequate protection for vulnerable users. So let's conclude our contributions. In summary, our study is the first to investigate user vulnerability in recommendation systems, and we find that well-fitted users are more vulnerable to attacks. Then we propose a simple but generable, effective adversary training method, VAT. It introduces user adaptive perturbations magnitude based on the vulnerability we find. Okay, finally, I would like to thank all the authors for their contributions to this work. And this is the end of my presentation. And now I can answer some questions if you have about our work.
All right.
Thank you.
Thank you. We don't have time, but please post your questions on Slido. And the next is a coffee break, and this is sponsored by Huawei. And there are also sponsors meetup from from OBS, Booking.com, and PopRex. Please try to visit them. Thank you. And the next session will start at 12 here.